Okay, all right. So today we'll be looking at the principle of mathematical induction. I believe this is either the second or third topic on the Pure Math Unit 1 syllabus. It is a relatively short topic, but the work can seem difficult at first, but once you get the hang of it, you'll be all right. So these are the three subtopics that I've listed here. We have sequences and series. We'll be looking at in notation for sequences and series, finding general term of a sequence or a series. Looking at summation proofs. You'll see what I mean in a second. These are kind of long, but it will be easy once you get the hang of it, as well as divisibility. So they're both similar. So the principle of mathematical induction, we would prove a series is true for all natural numbers, whatever have you. And we also prove a division. So we prove that some statement is divisible or a multiple of some natural number for all natural numbers. Okay. So first, before I start, let's talk about the principle of mathematical induction. So a definition I have, let me just type it up here, is that the principle of mathematical induction, often abbreviated PMI, is a method of mathematical proof that is used to establish that a general statement or proposition, as I was telling you before, so basically in a question they would give you a statement, you have to prove if it's true or false, is true for all natural numbers, or otherwise known as positive integers, or is true for all members of an infinite sequence of natural numbers. There's a lot of words, but basically what we're saying, as I was telling you before, is that they'll give you a set. They'll tell you for all natural numbers or whatever have you, or all positive integers, same thing. Let me finish what I was saying. Numbers, right? So they'll give you a set and they'll give you a statement. So a proposition is basically a statement that is either true or false. So you are going to be required to prove that this statement that they give you is true or false for the set that they give you. So the set of numbers that they give you. All right. So I'm just going to list the steps. So it's a repetitive process. So every time the more you do it, the better you get at it. So the first 4 steps are basically robotic. So the first thing you have is the proposition. So the proposition they give you, this isn't a required part, but I like to put all these steps so that you can understand properly. So the first step I'll say is the proposition. So that is you be restating what they gave you, the question they gave you. Second step is what we call the base step or the initial step. So this is where you prove for like the first element inside of the set step. So we basically, the proposition is where you restate the statement they give you. Then the base step is where you prove the proposition to be true or false for the first element in the set. The first element in the set. Okay? And obviously, if it isn't true for the first element in the set, then you know it's not true for all. Because for it to be true for all, the proposition to be true for all, it must be the case for all, every single last natural number or whatever have you, whatever set they give you, it must be true for every single one of them for the statement to be true. So if you come to the base step and you realize, well, that's not true, you automatically know that is not true for all. Does that make sense? A little?
Yes, yes, please, so far.
Okay. When we do an example,
Yeah.
you can see. Alright, so next
Okay.
one is the induction assumption. Okay, this is where, now this part maybe, you may not understand this part fully. But basically, if you think about it, numbers don't stop. We don't like stop at a million and don't go after that. We go to 2 million, 3 million, 100 million, billion, trillion, whatever have you. The numbers keep going on and on and on and on. So if you think about it, it'll be tedious and borderline impossible to sit down there and prove a proposition for every single element in the set. If the set is infinite, you'll be there forever, if that makes sense. So what we have to do is we usually use the letter K, but you can technically use any letter you want, letter K to represent an element in that set, because you cannot sit down and prove for all. But you'll use K, which will be the generic element, which will represent all the elements. So as long as you use that, you're basically proving for all, but not actually proving for all, directly at least. But we will get to that point. So K. So the next part is where you prove for K plus 1. So after we have the generic element K, we must prove for the element directly after it, which should be K plus 1. If you think about it, let's say we have element 2. The element directly after is 3. And if we use it like this, right, this step is called the induction hypothesis. So this is what we will actually have to prove. Induction hypothesis. That's where we will prove for K plus 1. If you think about it, if you prove for 1 as K, K plus 1 will be 2. And then if you put 2 as K, K plus 1 will be 3. So you can see a pattern happening. So if you prove for K, if you assume for K, then prove for K plus 1, you'll be proving for every single element in the set. Because as I said before, the set is infinite. It doesn't stop. So if you prove for the generic element K and the one directly after it, that means that every single element, because everything is infinite, so it'll be forever going. So every single element in the set will be proven for, so the statement will be true. And then the second last step, so this is really and truly really proof actually begins. Got to this point, it's kind of robotic. You'll be rewriting basically the same thing each time. The next thing is the actual proof of the induction hypothesis. The induction hypothesis. And the last step is the conclusion. So basically, as soon as you've proven, so this is basically what you're stating. You're stating this is what I need to prove to show that this whole proposition is true for the whole set. This is the actual proof here that you actually do. And then as soon as this is true, that means that you know. So you just state that it is in fact true for the set. As I said, we'll run through an example. Okay, so let me pull up an example. Alright, so I'll find an easy one for us to do. Alright, I have an easy one here. Okay, so let's say given S, I don't know, given, let me insert an equation here. Given R is equal to 1 to N of R, we need to show that this is equal to N plus 1, I'm going to make it bigger, N plus 1 over 2 times N. Okay, so you're given this. Okay, so given that the sum of 1 to R is 1 to N of R is given this, we need to prove that this is the case for all natural numbers. You'll see something like an upside down A, and basically that means for every element. So for every n and a set of natural numbers. Every element is a set of there you go, natural numbers. Okay, so this is the question that's given. So let's look back at our steps. So they're giving us the proposition. We'll restate it. So no proposition. So I'll say let S of n I'm gonna copy this back. So I'm gonna say let S of n. So I'm saying let S of n be all this. Okay, this is what we're proving. Okay, so I'm saying let S of n. So let S of n, which is the sum of r to n of r, equal this. N times n plus 1 all over 2. So this is what we have to prove. Okay, so that's the first step. Second step now is where we actually, the base case, to prove for the first element in the set. So since it is a set of natural numbers, can you tell me what would be the first element?
Would it be 1?
Yes, please, it will be 1. Okay, so what we will do, wherever we see n, we will plug in 1. Okay, we replace it with 1. So I'll say, equation s of 1, which is the first element, that'll be our base case. So we replace, every we see n, so there's an n here, above the sigma sign. So I can replace that with 1. And there's a 1 here, sorry, an n here, so replace that with 1. And there's an n here as well inside the bracket, so replace that with 1 as well. Okay, that's all we're doing for this first part. We're not done yet with this part though. So the first thing we did is we replaced every single element with 1, which would be the first element. If they said for every n is set of natural numbers where n is greater or equal to 2, then the first element would have been 2. So then we would have replaced every single n with 2. Does that make sense?
Yes, please.
Okay. At any point if you feel lost or overwhelmed, just let me know so if I can explain it better. So, right, so the first part we replace every n with 1. So we have to simplify though. We haven't proven that it is though. We just substituted. So, new equation. So when I plug 1 over here, the sum of 1 to 1 is just 1. So that'll be 1 over here. 1 is equal to, and 1 plus 1 is 2 inside the brackets. 2 times 1 is 2, and 2 over 2 is 1. So since both sides are equal to each other, we'll say that the left hand side is equal to the right hand side. Therefore, symbol, not saying it. I'll just raise up the words therefore. Therefore, this is true. So we'll say therefore S of the 1 is true. So we've proven that for the first element in the set, it is true. Following me so far?
Yes, please.
Okay. So we've done our proposition. We've done our base case. Next thing to do is our inductive assumption. So basically, we'll be doing the same thing here. Wherever we see n, we'll plug in k. We replace it with k. So I'll say now, wait, let me start a new equation. So I'll say s of k this time. Paste it here. So everywhere I see an n, I'll replace it with k. So this will be a k. This will be a k. And this will be a k. Okay? So we'll state that we need to assume that S to the k is true. Okay, that's why it's called the inductive assumption, because we're assuming that this is true. Okay, so we'll use this later down when we're proving our hypothesis. So this is the end of this step. So we assume that the S to the k is true. So the next step, according to what we wrote above, would be the inductive hypothesis. So similarly what we did with the previous two steps, we'll replace n with k plus 1 this time. So let me just start a new equation. So we'll say S of the k plus 1. So wherever we see n, we replace it with k plus 1. And over here, we replace this. The first n on the outside of the bracket, that would be k plus 1. So I'm just going to put it in brackets. K plus 1 to show that we're multiplying. And then in here now, don't forget we have another one over here. So we replace n with k plus 1. We'll have k plus 1 plus 1. And 1 plus 1 is 2. So really and truly, we just have k plus 2 inside this bracket. You still with me?
Excuse me, please. One question, right?
Uh-huh.
After the class, how long will the recording take to be available?
I am not sure. That's not my area. What will happen is I will send it to a student advisor. That's their area they post it. I believe they post it within 24 to 48 hours. But I'm not entirely sure.
Oh,
I'll check on it for you.
okay, thank you.
Alright, so but you understand this part where we plug in k plus 1.
Yes, please.
Okay, just making sure. So we're gonna say now required to prove, spell required wrong, my bad. Required to prove that this k plus s for the k plus 1 is true. Okay, so this is the actuals. Up to this point, we haven't really done anything, We just stated the proposition. We proved for the base case, which was simple. We just plug in 1 where we saw n. We assume for k, and now we're just saying that we are required to prove for k plus 1. Alright, so this is where the actual proof actually begins. So now, we're going to say that s to the k plus 1 is equal to, but one thing you need to remember here, that the sigma is represents summation. So, alright, let me just go aside here so you make sure you understand this part. So if I said the sum of the first first 5 terms in a set of natural numbers, right? So that would be 1 plus 2 plus 3 plus 4 plus 5, right? So that would be written as, if you write it using sigma notation, I would say, let me find this sigma, okay. I would say r is equal to 1 to 5. I'll say r is equal to 5 of r, right? And that would be the same thing as this here. You understand that part?
Yeah, but I have a question, right?
Uh-huh.
So, for instance, if I put the 1 where the 5 is and the 5 where the 1 is it considered correct, or that's still how it's supposed to go?
Usually you write the smaller term at the bottom. Usually you write the smaller term at the bottom.
Oh, okay.
Right. Right. So you understand this part though. So this is the same thing as this.
Yes, please.
Okay, good. So if I told you, so if I asked you, right, if the sum of the first 4 terms in a set of natural numbers, if I asked you, so I said if r is equal to 1 to 4, right? And I asked you of r, So you would agree that that would be just the first four of these numbers, right? The sum of these first four numbers.
Yes, sir.
Okay. Now if I ask you if this, so if we added 5 to both sides, so if I copy this, so if we added 5 to both sides, so the sum of r is equal to 1 to 4 of r plus 5. Let me do it separately so I don't confuse you. Let me put this in brackets. So if I said the sum of that plus 5 is equal to this first line here, would you also agree? If we added 5 to both sides of this line here?
Oh,
Pardon?
no, I don't think so.
You don't agree? Why don't you agree?
Um, because okay, you said that the including the four and the one below, right? And plus the five
Mm-hmm.
equals to 1 to 3 plus 4 plus 5. Wait, so wait, the 5 on the well on my left hand side.
Mm-hmm.
Is that only a part of before the bracket? Is that just it before the
The
bracket?
5
Or you
isn't
include
the
it?
reason why that's why I did it like this. So I put the summation inside the brackets because that's separate from this. So if you know bond mass, we'll deal with the
Oh,
brackets first. So this is just the
oh, oh,
summation from 1 to 4. But then when we've done that, we're going to add 5 to it. That's what that means.
oh, oh, oh,
Right? It's not a summation of r plus 5. You,
oh. Okay,
you understand?
right.
Alright, so if we take this line here and we add 5 to both sides, you agree that this would be the result here.
Yeah.
Okay. So I now might ask the question. So if this is equal to 1 plus 2 plus 3 plus 4 plus 5, and this is equal to 1 plus 2 plus 3 plus 4 plus 5, can I say that this is the same thing as this?
Yeah, I actually think so.
Right, yeah, you'll be correct because it's the same thing. So how you can look at it, and I want you to look at it, is that if this is, so let's replace, so let's say that 4 is n, right? So let's say that 4 is n. No, 4 is n. They want to replace it with n. Yeah, okay. Let's say that 4 is n. So let me replace n, 4 with n wherever I see it, okay? But 5 is the same thing as 4 plus 1, correct? So if I replace this with n plus 1. So if we said that let n, and delete this, put this in brackets, n plus 1. Okay, so if I let, still looking at these two, so if I take this, and I said I take this, right, and I equate them, like how we did just now, and I said let 4 now equal to n, do you still agree that this is equal to this?
Hmm. This is the pattern now law, so you
Okay,
can go over it one more time, please.
okay,
Thank
okay.
you.
Alright, so let me rewrite it. So we said, right, so back from the top. So we said that r is equal to 1 to 5. The sum of that, of r, is this up here. The sum of 1 plus 2 plus 3 plus 4 plus 5. Right? And we went on to say that the sum of 1 to 4 is this. 1 plus 2 plus 3 plus 4. Right? And I asked you, if we add 5 to both sides, right, we would get this as a result. So if we look at the right hand side in both, let me move this here. Let me move this right here. So if you look at the, move this over here. Okay, so if we look at this, so if we said that r is equal to 1 to 5, sum of that of r is this, and we said that this is also the case here. So if this is equal to that, so can't we equate them to say that r to 1 to 5 is the same thing as this? Or if you don't understand that example, let me use a different one. So let's say that, okay, let's say that 2 plus 3 is equal to 5, right? And let's also say that, let's say 10 divided by 2 is also equal to 5. So if 2 plus 3 is equal to 5, and 10 divided by 2 is equal to 5, we can say that 2 plus 3 is equal to the same thing as 10 divided by 2. Because we can simplify both sides, and we can say 2 plus 3 is equal to 5, and on the other side, 10 divided by 2 is equal to 5. And the left-hand side is equal. That's what LHS stands for, left-hand side, and RHS is right-hand side. So if we have both things being equal on the same side of the equals, on the both sides of the equal sign, that means they're equal. Correct? You agree with this part?
Yes, please.
Right. So the same thing here. So we said that, okay, we have r is equal to 1 to 5 being equal to this. The sum of 1 plus 2 plus 3 plus 4 plus 5. And we also said if we added 5 to both sides, we would get this. So if both of those are equal to the same thing, that means we can equate them and say they're equal. So the sum of 1 to 5 of r and the sum of 1 to 4 of r plus 5 when it's finished will be equal to the same thing. Now I'm saying this part right here is what I want you to see, is that if we let 4 be equal to n, so wherever we see 4, we will put n, right? So there's a 4 on top of here, on top of the summation. So I'll replace that with an n. We also know that 5 is the same thing as 4 plus 1. So if we said that 4 is equal to n, we can replace 5 with n plus 1, which is the same thing as 4 plus 1. And the same thing here with n plus 1. Still not understanding? Still not clicking?
Yes, please. For somehow this part is kinda, troubling.
Alright. Alright. So let me see if I can explain it differently. Or another way we could look at it, right, is if we take back up here this first line. So you agree that this second line is true. The r is equal to 1 to 4 of r is equal to this. 1 plus 2 plus 3 plus 4. But if you look here, this is the same thing as this, right? So we could replace this. 1 second. Right, sorry about that. Right, so if we said that 1 plus 4, 1 plus 2 plus 3 plus 4 is equal to this, right? That means wherever we see this, we could replace it with this, because they're the same thing. So I could take this and put it here. I can replace this part with that. Because they're the same thing. As long as they're the same thing, I can use them interchangeably. So if this is equal to that, and this is equal to this, then I can just put it in, which is the same thing we have down here. So all we're doing is that we're saying that we're just replacing something we already know. We already had this, and this new thing here. We're just trying to express the new thing we have in terms of something we already had before. That's all we're trying to do. That made a little bit of sense now, or are you still lost?
Yeah, I understand that part,
Right.
when
So wait,
when
so you're
replacing
not
and stuff.
understanding the part where we replace it with ends.
Yes.
Oh, okay. All right. So if we let, okay, all right, so we agree that this is equal to this, right? So now I'm saying take that, but let n represent 4. So let's replace 4 with n wherever we see 4. Okay, so I say let n equal to 4, right? So wherever we see 4, we replace it with n. So we're looking back at this top line here. But what I'm saying, right, so this 4 here, we can replace that with an n. That's what we did here. Replace the 4 here with n, right? But we still have 5s here. We still have 5 on top of here and 5 over here. But 5 is the same thing. So if 5 is equal to 4 plus 1, and we let n equal to 4, we're basically saying that 5 is equal to n plus 1. Follow me with this part?
Yes, please.
Okay, so right, so we let 4 equal to n. So wherever we see 4, we replace it with n. And since we know that 5 is the same thing as 4 plus 1, then 5 will have to be n plus 1. So that's basically what we did here. We wrote this part in terms of n is equal to 4.
Oh, okay.
Oh, wait, now click. You now understand.
Yeah, no, understand.
Okay, okay. Everybody else covered? I see about 2 more people. So everybody else covered?
Yes, sir.
Okay, just making sure. All right, so this is the part right here that I need you to understand for the next part of the principle of mathematical induction, right? So if we go back up here, we now have to prove s to the k plus 1, right? But we just said down here that s to the, so let's say that this, so let's say that, all right, we look over here, look back up. We said this is equal to k plus 1, right? So let me move it over here so we can look at it at the same time. Let me copy it down here. So let's copy this. Let's copy this, okay? Let me go on a new page. All right, so let's paste that. So that's what we're proving right now. This part here that we just went through, okay? So, okay, so we just said, so let's say that this is the same thing as, let's say that this is the same thing as s of n plus 1. Okay, so let's say you can see that these are the same thing here, just that we replace the, so if this is s to the k plus 1, right? It should be the k plus r is equal to 1 to k plus 1 of r. So the same thing will be here. So s of n plus 1 is the same thing as 1, r is equal to 1 to n plus 1 of r. We can see that they're basically the same thing but different letter. We can see that, right? Hello? We can see that this is the same thing as this, just is a different letter.
Yes, sir.
You sure?
Yes, sir.
Okay, just making sure. Right, so we can see that this is the same thing as this. So if we said that r is equal to 1 to n plus 1 of r is this, that means we can rewrite this the same way. So let's say, all right, so let's say that this, let's copy this. So if we were to rewrite it similarly to how we have it there, we can see that to be r of equal to 1 to n of r. So we can write this back over here. So let me just write this part. Just replace the n with a here. Right. So if I was to write it like this, right? So wherever we see n, we replace it with a k. If I write it like this, k plus 1. So do you agree with what I did there? I basically replace the ends with k. Not hearing a response. Do you agree with what I did there? So I said that these are basically the same thing, just a different letter. And if we just establish that so the sum of 1 to n plus 1 is the same thing as the sum of r is equal to 1 to n plus n plus 1. So if we have this here, this first part, don't worry about the second part, we're going to get to that. So if we have this first part here, then we can rewrite it like how we did the second line. Do you agree with that?
Yes, sir.
Okay. So basically what this line here means is that the sum of 1 to k, whatever k is, plus the next term right after k, which would be k plus 1, is the same thing as the sum of 1 to k plus 1. So if we were to write it out, just so you can solidify this. So let me say that the left-hand side, which is the sum of 1 to k plus 1, let's say that is 1 plus 2 plus 3 plus 4 plus 5 plus 6, and on and on till we get to whatever k plus 1 is, sorry. So we get k plus 1. Right? And we also said that over here, that the sum of 1 to k will be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus on and on till you get to k. But we also said we also got this little part here. So whenever we're done, we're going to add on that part there. Right? You can see that? We just expanded it so that we can see the summation. Follow? Okay, she thinks it's in. Alright. So essentially, this is the same thing as this, as we established before. So, so this is the sum of k. This is the same thing as the sum to k plus the k plus 1. So this is the same thing. So I said all of that, and we're all around the world. So basically say for our next step, that we're trying to prove k, that's the k plus 1. Right? So we just established that we can rewrite that as this. The sum of the k, the 1 to k plus the k plus 1 term. Right? So we can basically write that there. So we said that this part right here, that would be the same thing as that. That's what I was trying to get to. So we're rewriting this so that we can get this. So we're saying that, sum of the k plus 1, which we represent, same thing as this. Now we have to get here to prove that this is the case. So if we look back up to our inductive assumption, we said previously that the sum of the 1 to k of r is the same thing as this. So, as I said before, as long as they're equal, we can replace them or use it interchangeably. So what I would do is that I would replace this with this. So then I would come here now and say that this, let me copy it, is the same thing as that plus k plus 1. All we did here is that we replaced this with what we stated previously. We assumed this is the case, that this is equal to this, and you can replace them. So what we're trying to get to is this right here. So as long as we can show that this, which is this right here, same thing as this, as long as we can show that this is equal to this, then we've proven that it is true. So the next step, we'll just simplify. So we made the substitution, now we're simplifying. So now we can factor out the k plus 1 and a half. All right, maybe do it one step at a time. So the first thing I'll factor out is the k plus 1. Okay, so let me factor that out. So then I'll get k plus 1, and then that would leave k on 2. K, let's say k over, let me put the fraction in. Put the k over 2. Alright, k over 2 plus 1. Alright, so all we did to move from this line here to this next line is that we factored out the k plus 1. So k plus 1 we factor out, that left us with k plus 2. And then when we factor out, this is the same thing as k plus 1 times 1. So we factored that out, that left us with 1. So now we will just rewrite this second bracket as a single fraction. Is equal to, write back the k plus 1. And that would, when we break this as a single fraction, you will multiply the second one by 2. So that'll give us k plus 2 over 2. As our next, when we write it as a single fraction, that'll be k plus 2 over 2. And as you can see from above, we have reached what we were supposed to reach. As you look here, we've proved it. So this is what we were trying to get to. So we basically proved that s of k plus 1 is equal to this, which we have proven here. Okay, so now that we've proven that, we can now conclude and say, hence, by principle of mathematical induction, and you would write the proposition you stated earlier. So you'll say that, hence, that by the principle of mathematical induction, oh no, the first, yeah, it doesn't matter, copy. So I write this over down here. So hence, by the principle of mathematical induction, we prove that S of n, which is the same thing as r is equal, the summation of r 1 to n of r is equal to n times n plus 1 all over 2. For every, I have to write down the last part, so we're saying that for every element in the set, so I write the sign, the upside down A, so saying for every n in the set of natural numbers. So just to recap what we just did, so this was the question I gave you. So we said that given this, the sum of r is equal to 1 to n of r, we want to show that this is equal to this for every n in the set of natural numbers. So from all natural numbers, so from 1 to positive infinity. So we'll say here now, so as I said, the first step would be the proposition. We restate it, so we write it in terms of s. We write it as the s, which makes it easier for us. So we want to have the writing over this all the time. So then we would first do our base case. So we put in 1, or the first element in the set is not always 1. You have to always look at the question they give you. So then you put in 1. Wherever you see n, you replace it with 1. So that's what I did here. Simplify, we realize that both sides are equal to 1. The left hand side is equal to the right hand side. So therefore this is true. That's our base case. So now after that we would do our inductive assumption, which is similar to the previous step. We just replace n with k where we see n, and we have to assume this is true. So once we assume this is true, we would reuse, that's why we assumed it, so we can reuse it later down here when we made the substitution. So after we assume, then we state what we actually need to prove, which would be s of the k plus 1. Okay, so we basically replace n with k plus 1 whenever we saw it, and we said we're required to prove that. And now we actually did the actual proof. So we said, as I was explaining down here, that we can rewrite the summation like this. That's why I went through all of that. So we can understand how I got from one step to the other. So then you would then write now this to write the sum of 1 to k of r plus the k plus 1 term. So the next term right after k, which should be k plus 1. So for instance, if you say that the k term was 2, the next term would be 3. And 3 is the same thing as 2 plus 1. So it will be the next term in the sequence. So then we will replace this with what we previously assumed, our inductive assumption up here. And once we replace it, we can simplify. So then I factored out the k plus 1, that left us with k over 2 plus 1. And then we simplify it right in as a single fraction, and you can see that this is the same thing as this. So we would have proven what we needed to prove. So then we had our conclusion. So we said hence for every n in a set of natural numbers that this is the case, that s of n where the sigma of 1 to n of r is equal to n plus 1 times n plus 1 all over 2. Okay, any questions? Dilly Dally, have any questions? Did it at least make some sense?
Sir, I think I got the last part more than the when you rewrite it as SK plus 1.
So you understand. So which part you understand? Which line lost you? This
About,
part, this line here.
no, no, I understand. I didn't understand how you necessarily got that, but I understand it to the last part there.
So you understand the algebra, but not the concept.
No, sir.
Okay. All right. So all right. So all right. Let me do an example here. Okay. So if we go back to what I was saying here. So if you think about it, the set of natural numbers is an infinite one. You start from 1, you go to 2, you go to 3, 4, 5, on and on and on. They don't stop. Numbers don't stop. We just start naming them after a certain threshold. So it would be impossible for us to do this proof with every literal number. So you can imagine someone sitting out there and trying to prove this with a million, then a million and one, and a million and two, then and on and on and on and on and on. They'll be there forever, their whole life. The numbers don't stop. So what we have to do to represent every single element in a set is replace it with the letter k. It doesn't have to be k, but we tend to use k. So we're saying that let k be an element, any element in the set of natural numbers, right? So if we so we're saying that k is the same thing as an element in the set. And k plus 1 will be the element directly after it. So for every and any element in the set, k, and an element directly after it, k plus 1, right? We're saying that this is the case. That's why we're proving for k plus 1. Because if you think about it, if k was 1, k plus 1 would be 2, right? And then if, let's say, we move to 2, that k is 2, then k plus 1 will be 3. So if we keep going on and on and on like that, because we can't sit down and take them in pairs like that. We can't say, all right, let k be 2 and let k plus 1 be 3. Let's prove for that. Okay? Because we'll be there forever. Then it'll be a million is a k, then million plus 1 is k plus 1. So we're saying let k be any and every element in the set of natural numbers, right? So we're saying that k, let me find the element sign, right? So k is an element, is a natural number, right? Because if you think about it, if we say k, it'll be k plus 1, right? And then k plus 1 will be our new k. So then k plus 1, which is no k plus 1, will be k plus 2. Because k plus 1 plus 1 is the same thing as k plus 2. Then k plus 2 will be our new k. So then we'll have k plus 3. So you can see a pattern here. K plus 3. So it'll keep going on and on and on. So what we're really doing with this proof is that we are indirectly taking every element in a set and a number directly after it in a continuous manner and saying this is the case. So we're indirectly proving it in a sense. So we're not literally taking each number, but we're taking a generic number and representing it. Is that any clearer, or did I lose even more?
No, I see the pattern, sir.
So you sure you understand?
Repeat, please.
You sure you understand the concept then, what we did today?
Yes, I think I get it.
So
I
if I
just need
give
to
you
read.
a question to do, you can get it done?
I'm sure if I rewatch the recording, I think I could do it, sir.
So you want me to do one more, or this is good for the evening? You want me to do one more before we leave?
Yes, sir, that would be fine.
Alright, so let me do another one, see if you can get the hang of it. You can talk me through it this time though. I'm just gonna write what you tell me. So let me see. That's on the page. Alright, so really quickly we're gonna I'm gonna find another simple one. Alright, so this one should be fun. So we have, so let's say given, so if I give you this, so given, so we write a new equation here. Alright, so given that r is equal to 1 to n again of r squared this time, makes it alright, of r squared. So given that, I want you to show me or prove that that is the same thing as n times n plus 1 times n times, 2n plus 1, all divided by, I believe the question says 6, all divided by 6. Okay, so this is the question here. So we want you to prove this. We want you to prove this for every, that's what the upside down, oops, wrong sign. That's what the upside down A represents for every element. So I'm saying, basically saying for every natural number. That's basically what this means. To every natural number. Okay? So if we look back at our note from before, above here, we said that the first thing we need to do is state it so that in a way that we can understand. So we're going to rewrite this. So we're going to say, let S of n be this first part. So let S of n be that first part. Okay? So the next thing we have to do is the basic step. So you're going to talk me through the basic steps. So what do we have to write?
Sir, you would replace n with the first number of the set, which would have been 1.
Okay, good. So we'll say S of 1. So we put this back. We replace n with 1. Okay, so then I'll replace these n's over here with 1. And we can put brackets to show that it's multiplication, right? So then we have to simplify to show it's actually the case. So when we plug 1 on this side, what will we get?
1 squared.
1 squared, okay. 1 squared is equal to, on the right hand side, right? So when we simplify that, you would get the first bracket 1 plus 1 is 2, and then 2 times 1 is 2 plus 1 is 3. So that's the same thing as 1 times 2 times 3, which is 6 over 6. Let's see. Right, which is 6 over 6. Okay. Right, 6 over 6. And we can see that both of these will cancel onto 1, correct? 1 squared is 1, and something divided by itself is 1. Okay, so we have shown that the left hand side LHS is equal to the right hand side RHS. So that means, therefore, S to the 1, which is what we just did, the base case, is true. Okay, so what do we have to do next?
Would we replace it with 1 with k?
Yes, please. So we would make our assumption basically. So as you said, we replace n with k. Okay, so looking here now, we're gonna replace all the n's with k. So this part is part that lose most people. We're saying that k will be any and every natural number, or to make it more general, every element of the set. Just it happens that this set we're given is natural numbers. That's what n stands for here. Sorry, that's what the n stands for. So we're saying that k will be a generic element of the set, any and every element in the set. Okay, so this is what we're saying here. So we're saying that the sum of every generic, so from 1 to the generic element, any generic element of r squared should be equal to this. But we're not too sure yet. We have to prove that. So that's why we're assuming. So we're assuming that that is the case. So we're saying we're going to assume it's true. Okay? So in the next step, what do we do after we made our inductive assumption?
I'm not sure. Would we
Alright, let's go back up to our previous one. So we did here, right, this is our base step here. Oops. Right, that's our base step. Then we assumed, and the next thing we did is right here.
Oh, so to replace it with k plus 1, and then we prove if it's true.
Yes, exactly that. So let me go back to the page. So as I said, right, we're letting k be any and every element in the set. So k plus 1 will be the element directly after it. So let's see. So let me say s to the k plus 1. So let me paste that. Paste that, right. So as you said, we replace n with k plus 1 everywhere we see it. So we k plus 1 here. And on the other side, we replace this with k plus 1, but brackets to show that we're multiplying. K plus 1. So the first n we replace it with, and we put k plus 1 in this bracket, that would be k plus 2 because there's the extra 1 there. So that would be the same thing as k plus 2. Right? But here now, you gotta be careful. BODMAS, remember. So we multiply the k plus 1 first. So k plus 1 times 2 is the same thing as 2k plus 2. Right? And then we're going to add the extra 1 to make it 2k plus 3. We're just going to do it on the side just to make sure you understand that part. So, right, so what we have is, what it was again, 2k plus 2n plus 1, right? So we're saying n is equal to k plus 1, right? So if we have the case where n is 2n plus 1, we replace that, that would be the same thing as 2 times n, which in this case is k plus 1 plus 1. We need to make sure we get this part correct. If we don't, we're going to find ourselves in problems later. So we're basically saying then that, right, when we simplify that side, we multiply the expanding brackets, we're going to get 2k plus 2 plus 1, and we add the extra 1, that's going to give us the 2k plus 3. Alright, just to be sure. Alright, so that's how we got that. So I would put that there. So that's the same thing as 2k plus 3. Right? So we're going to say we're required to prove this. To prove that this is the case. S of the k plus 1. Right? So now we're actually doing the proof. So before we just been replacing n with 1, k plus 1. Now we're actually doing the actual proof. So we're going to say no. We're going to say no. S of the k plus 1 is equal to, and don't forget what I was doing earlier, we could rewrite this. So we're saying, so basically what we're trying to do, we got the sum from 1 to k plus 1. What we're saying, right, that would be the same thing as the sum from 1 to k plus the k plus 1 term, right? So that would be this first part. So that would be the sum of 1 to k, right? And we're going to add on to that the k plus 1 term, the next term that would have been in the sequence. So if we were to, what would be the next term? Let me ask you that.
The next term would have been, so would you write it with the summation sign or the other side?
No. This is the, all right. Okay. So the sum, we already took care of the first part of it. That would have been, so this is the sum from 1 to k plus 1. Let me say that would be 1 to 5, right? So we're saying that the sum from 1 to 5 is the same thing as 1 to 4 plus what? What would we have to add to that to make it the same thing? The next term, right?
The next minute, yes, sir. So the k plus 1.
K plus 1, but look here. What's the thing here? You can see is a r squared.
Yes, sir.
Right, so the k plus 1 squared will be the next term. You understand that?
Not sure.
Alright, so we're gonna break that down in a second. Let me just finish writing this. Alright, hold on. Give me a second. So that's the same thing we said as k plus 1 all squared. Alright, so we need to understand this part before we can move forward. So, alright. So it's the sum of r squared. So basically, if you look at it, so every time we have an r, we're going to square it and add it onto the sum, right? So the first one is 1. So the first term will be r squared. Because don't forget, the sigma just represents sum. So every time we get a new term, we're going to add it on to the rest of them. And this, the 1 down here will be the starting point. Because the other student asked me before if you can have the 5 at the bottom and the 1 at the top. No, because we're saying that the sum, we're starting from 1 and we're going to 5. But in this case, we're saying k. So the starting point is 1, the end point is k. Because we need to know where we're stopping. So we're saying that the sum here, the sum of every element between 1 and k inclusive, we're going to square it and add them all together. So you would have 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, on and on and on till you get to k squared. Because if you look back down here, or the previous one, like here for instance, we said that the sum is the sum for r is equal to 1 to 4, right, of r. So you always have to look at this. This is the general term. This is basically what are you adding. You're not adding the numbers themselves. The numbers are just the input. But in this case, the input is the number itself. So it is the sum of r. Because you can see the first one here is start point is r is equal to 1. That's why the first term is 1 here. And the last one is 4. That's why the last term here is 4. And everything in between we fill in the parts. That's what the summation is representing, everything in between. Okay? So if we have it with the r squared, that'll be the same thing as the 1 squared not sure where that's from. Oh, clicked on the wrong thing. That's the same thing as 1 squared plus the next term, which should be 2 squared and on and on and on until we get to k. That's the stop point. That is our ending point there. So you say k squared. You follow me or no?
Yes, sir. I see it.
Okay, just making sure. You need to understand before you can understand the proof. So that's why I have, you always have to look at the general term. General term here. That's telling us what we're actually adding. The limits that we will call them here, the 1 and the k plus 1, the 1 will be our start point, k plus 1 will be our end point. And the general term is what we're actually adding. So what we're actually doing to our inputs to this. So this will be the next term. So the next term will be the k plus 1, which is the ending point. We have to square it and add it to the others. So we understand that part. So now we're going to look back before our assumption. We said that the sum to the first k terms, 1 to k, so the sum just before we get to the last term, is the same thing as this. So since we're assuming they're equal, we can use them interchangeably, which means I can replace one with the other. Okay? So let me start a new equation. And I'm going to say that this is the same thing as, I want to replace the sums of 1 to k of r squared. I'm going to say that plus, we can write back the other term, plus this term here. So we just replace the first term. You understand?
Yes, sir.
Okay. So we just replace it. So now this is the part that other people get tricked up with. It's like your algebra has to be good. If you don't know how to manipulate the terms to get what you want, because if you look here, this is what we want right here. If you don't know how to manipulate terms, you're going to find yourself in trouble. You're going to get stuck. So you have to be able to manipulate what you have to get what you want. Okay? So always look at what the endpoint is. So we want to have it like this. K plus 1 or times k plus 2 times 2k plus 3 all over 6. Right? So right, so I'm going to look at both terms here and I'm going to see what I can factor out. I can see that in the end I want a k plus 1, right? So I'm going to factor out, I can see that I can factor out k plus 1 from both because I can see it in both. There's k plus 1 square here and k plus 1 at the top here. So I can factor out k plus 1. We can do it one step at a time. So I can factor out the k plus 1. Equation. Alright, so after I factor out the k plus 1, that would leave me the first term be left with k times, k times k plus 1. That'll be all over the 6. That's the only thing we did, we factored out. Then the other term, k plus 1 squared, all squared. When we factor out k plus 1, that leaves us with k plus 1. When you square something, you're multiplying it by itself, so we can remove it from there. Okay? So the next thing we're going to do here is that we're going to write this as one fraction. This second bracket as one fraction. Okay? So start an equation. We're going to keep our k plus 1 on the outside because we already have that. We just need to get this part here, the k plus 2 times the 2k plus 3 over 6. We need to get that part. We already have the k plus 1. So now, as I said, we're going to write this as a single fraction. So you multiply the second one by the denominator, which is 6. So that will give us, a single fraction. So that would be k times 2k plus 1 plus 6 times the k plus 1 that we had before, all over, all over 6. Alright, so what we basically do is simplify the numerator. Okay, so we can now go to the next part now. So we'll simplify the numerator. Right, so we'll expand the brackets. And you'll see that we will get a quadratic. So let me just write this back. Oops. Alright, so So we expand the brackets. So when we expand the brackets, we're going to get k times 2k will give us k 2k squared. So I'll give us 2k squared. So 2k squared. And when we look back up here, so k times 2k is 2k squared. And we multiply the k by the 1, it give us k. So it's plus k. Then in second bracket, we multiply 6 by k, we get 6k. And then 6 by 1 is 6. Right. Alright, good. So we expand the brackets. Now we need to simplify this. Alright. So what I'll do is that I will simplify it because I have 2k terms here in the middle. Alright, so that will give us 2. So I erase it back. Algebra has to be good to do this. You gotta be able to manipulate terms. So now when I simplify that, I'll just have 2k squared plus, that's supposed to be a plus in between there, 7k. Remove this one. Alright. Right, all we did is we added two like terms. Right. So next thing I'll do, so we can see it better, is I can move the 6 on the outside. So that is basically, we have a quadratic divided by 6, which is the same thing as the quadratic times 1 on 6. So I can move that to the outside. Right, so I'll say that, if I rewrite this line here, rewrite this line here. So if I rewrite this, I can remove the 6 from the bottom, and I can put the 6 on the outside. So I can say times 1 on 6 on the outside, and that'll leave us with just the quadratic on the inside of the third bracket. Here, 2k all squared plus the 7k plus the 6. Right, and we will factorize the quadratic as normal, but don't forget what we're trying to get. So now we have the, right here, so we have the k plus 1 and we have the 1 on 6. So we just need to get the k plus 2 times the 2k plus 3. So I suspect when we factorize the quadratic, that's what we will get. So we just need to factorize now, and we should be finished. So I'm going to factorize this now. Alright, so let me write back everything we had before. So when I factorize this, I need to get two numbers that when I add them, I get 7, and when I multiply, I get 12. So what would those two numbers be?
4 and 3.
4 and 3. Yeah, that works. Yeah, 4 and 3. Okay. So, okay, plus 3k. Right, so if I simplify like normal. Alright, I just copying because I don't feel like typing it over. So let me see. Copy. Alright, so right, so then we will factor out 2k from the first pair. So we'll have 2k on the outside, so I get rid of this square. Alright, so the 2k on the outside, and that will leave k plus 2. K plus 2. Just get rid of all this. Right, so that'll be, right, yeah, 2k, like 8k squared, right. Now in our second pairing, I'll factor out 3. Yeah, I'll factor out 3. Right now, okay, there's 2 here. Right. So now, as usual, we'll factor out the common thing again. So it should be k plus 2 in this instance. You can already see that what we're going to get. So, the equation equal. Alright, so let's copy this. Alright, so when we factor out the common thing, we'll be left with k plus 2 times, let me just get rid of all this, k plus 2 times, right, when we factor out the common thing, we're left with 2k plus 3, right, as you can see, this is what we wanted. But let me just write it in the correct form so I don't confuse anybody, so let me write it in the correct form. Well, not correct form, but let me write it in the same form that it was given in. So if we were to rewrite this now in the same form, we would get the k plus 1 times, they were all multiplying, the k plus 2 times the 2k plus 3 all over the 6, or in other words, times the 1 on 6. So as you can see, we have, let me just write an equal sign, equal, okay, good. So this is what we have here. And as you can see above, that is what we wanted to prove. The k plus 1 times k plus 2 times 2k plus 3 all over 6. That's what we wanted to prove. And since we got here, we showed that the SCD k plus 1 is in fact equal to this. We can say now, our conclusion. We'll say hence, by, or in other words, using the principle of mathematical induction, we were able to prove that that was in fact the case, our proposition. So we were able to prove that this was in fact the case. Okay, let me just write the ending part that they gave us. They said that we had to prove this for every natural number. So we did in fact prove it for every natural number. Okay, and we are finished. So we did everything we were supposed to do. We rewrote it in a proposition in a form we can understand. And here we did the base case. So we proved that it was true for the first element in the set, which is not always 1. You have to look at the set. I could have said for every, I could easily change this to for every, I could have said for all natural numbers, but where n is more than or equal to 2. I could have said that, or more than or equal to 3. So whatever. So usually if they give you like this, it will start from 1 because that's the first one in the natural set. But if you see something like this, always use the number they give you, reading notation properly. But in this case, it was 1. So we prove for our base case, we prove that it's true. And we assume for our generic natural number, which is k. Then we stated what we needed to prove for k plus 1. And we actually proved this. This is long part. That's why I said the first 4 steps are pretty robotic. So you would state it as an n. In terms of as an n, you would plug in the first element. You replace with k. You replace with k plus 1. You do that every single time. Then here now, where most people get stuck is the algebra. You're going to be able to move from one point to the other. So you can see we went through a lot of steps. We started with this. We substituted with our assumption that we made earlier. And then we use algebra to reduce it down to this, which is what we needed to prove. And since we proved it, we can say that, yeah, it is in fact the case. Okay, any questions?
No, sir. I think I get it.
I think you'll get it. All right, I'll give you some homework then. All right, so I'm going to
Okay.
stop the recording now.